We know that if we connect a p-n junction diode to a battery with the p side connected to the negative terminal and the n side connected to the positive terminal, the diode is said to be reverse biased. A reverse biased diode allows little or no current through it. According to the IV characteristic of a p-n junction diode, the current through a reverse biased diode changes very little with an increase in applied voltage, and it remains almost constant. The value of this current is called the reverse saturation current. Let us see what happens when we increase the applied voltage across a reverse biased diode after it attains the reverse saturation current stage. We observe that the current through the reverse biased diode suddenly increases for a specific value of applied voltage. This phenomenon is called breakdown of the diode. Diode breakdown occurs because a high applied voltage creates a strong electric field that results in the breakage of covalent bonds in the p region. The electrons released by this breakage of bonds have enough energy to enter the n region, resulting in a large increase in current through the diode. The emission of these electrons from the host atoms due to the high applied voltage is called the internal field emission or field ionization. The voltage at which there is a sudden increase in current in a reverse biased diode is called the breakdown voltage. A diode designed to have low breakdown voltage under reverse bias is called a Zener diode, which is named after its inventor C. Zener. A Zener diode is made by doping both the p and n sides of a p-n junction diode heavily. The circuit symbol of a Zener diode is represented as shown. Although it is similar to that of a p-n junction diode, the major difference is that the two small projections in opposite directions are added to the line on the n side of the p-n junction circuit symbol. The pointed edge of the triangle indicates the n side of the diode, and the base of the triangle indicates its p side. Beyond the breakdown voltage, even an insignificant change in the reverse bias voltage can produce a significantly large change in the current. This implies that the voltage across the Zener diode remains constant, even though the current through it varies widely. Thus, a Zener diode can be used as a voltage regulator to convert a variable voltage input into a constant voltage output. Here is a simple circuit used for converting a variable voltage input, say, from a rectifier into a constant voltage output using a Zener diode. The input voltage is connected to the Zener diode through a series resistor having resistance R with the Zener diode in a reverse bias arrangement. A load resistance is connected parallel to the Zener diode to collect the constant voltage output across it. The current through R is equal to the sum of the Zener current and load current. If the input voltage in the circuit is increased, the current through R and the Zener diode increases. This causes an increase in voltage across R without a change in voltage across the Zener diode. This is due to the fact that beyond the breakdown voltage, the voltage across the Zener diode remains the same, although the current through it changes. On the other hand, if the input voltage is decreased, the current through R and the Zener diode decreases. This reduces the voltage across R without affecting the voltage across the Zener diode. Thus, irrespective of increase or decrease in the input voltage, the voltage across the Zener diode remains constant, which is collected across the load resistance. Hence, the Zener diode acts like a voltage regulator. The choice of the Zener diode depends on the required output voltage. Zener diodes are available with output voltages ranging from a few volts to hundreds of volts. In order to provide good voltage regulation, it is essential that the current through the Zener diode is several times higher than the load current. This is done by selecting a suitable series resistance R that ensures Zener current in the circuit is several times higher than the load current. Optoelectronic junction devices are PN junction devices which work because of the current carriers that are generated by photons. Photodiodes, light-emitting diodes, which are referred to as LEDs in short, and solar cells are examples of optoelectronic devices. A photodiode is a device that is used to detect optical signals. It is a photodiode in your TV set that allows you to operate your TV using a remote. A photodiode is a specially fabricated PN junction diode with a transparent window that allows light to be incident on the diode. We know that light consists of tiny bundles of energy called photons, whose energy in turn depends on the frequency of the light. We also know that electrons in the semiconductor atoms of a diode need to overcome an energy gap to become free and create electron-hole pairs that act as charge carriers in the diode. When photons of light with energy greater than the energy gap fall on the diode, the photons get absorbed by the semiconductor atoms, leading to the creation of electron-hole pairs in the diode. A photodiode is designed so that the maximum number of electron-hole pairs is created in the depletion region around the PN junction. We know that the depletion region has an electric field created due to the separation of static charges on both sides of the PN junction. As soon as an electron-hole pair is created, the electric field across the depletion region pushes the hole towards the P side and the electron towards the N side. Due to this movement of charge carriers, a small photocurrent is generated through an external load connected across a photodiode. The magnitude of the photocurrent increases with an increase in the intensity of the incident light. However, this change is too small to be measured in the absence of any external bias. The magnitude of the photocurrent is too small compared to the large current that flows through the diode under forward bias. Thus, the change in photocurrent with change in the intensity of light is very difficult to measure when a diode is operated under forward bias. However, the change in the magnitude of the photocurrent with the intensity of the incident light can be measured when a small current flows through the diode under reverse bias. Thus, a photodiode is always operated under reverse bias. The IV characteristics of a reverse biased photodiode for different intensities of incident light are shown here. A light-emitting diode, or an LED, is a device that produces photons of different frequencies of light. An LED is a specially fabricated, heavily doped PN junction diode encased in a transparent cover which allows the emitted light to shine through. An LED is operated under forward bias, which increases the diffusion of minority charge carriers across the p-n junction. This leads to the recombination of the electron-hole pairs, which results in the liberation of energy in the form of photons. The energy of the emitted photons and the color of the light produced depends on the nature and the band gap of the semiconductor material used in the LED. Here is a list of some semiconductor materials used in LEDs of different colors. LEDs offer several advantages listed here over conventional electrical light sources: low operational voltage and power consumption, instant on-off switching without any warm-up time, source of near monochromatic light, long life and negligible wear and tear. LEDs have low reverse bias breakdown voltages. Thus, care must be taken that they do not get connected in reverse bias across a high voltage source. Now let us consider a solar cell. A solar cell is a device that converts light energy into electrical energy. The solar panels that you see connected to solar power appliances are made of a large number of individual solar cells. A solar cell consists of a thin, flat wafer of p-type semiconductor on which a very thin layer of n-type semiconductor is grown to create a p-n junction with a large surface area. The back of the p side is coated with a metal to form a metallic back contact. The top of the n side is provided with a metallic grid contact that covers only a small percentage of the total exposed area of the cell. A solar cell works when light is incident on it from the top over the n side of the device. A solar cell works on the same principle as that of a photodiode, where incident light generates electron-hole pairs in the depletion region of the p-n junction. As in a photodiode, the holes are pushed towards the p side and electrons are pushed towards the n side due to the electric field in the depletion region of the solar cell. The holes pushed towards the p side are collected by the back contact, while the electrons pushed towards the n side are collected by the grid contact. This collection of charges makes the back contact positive and the grid contact negative and gives rise to a current when a load is connected between the two. Unlike a photodiode, a solar cell works without any external bias. The large surface area of the p-n junction in a solar cell generates measurable photocurrent, making it a source of electricity. However, just like a photodiode, the photocurrent produced by a solar cell depends on the intensity of the incident light. If we plot the intensity of solar radiation against its energy, we find that the maximum intensity radiation is produced by photons having energy equivalent to 1.5